So when it comes to analyzing transistor-based circuits, imagine that you have a bunch of transistors and a bunch of resistors and capacitors connected to them, right? It is sometimes, it turns out to be very useful to have a simpler model of the transistor based on the current expressions that we just discussed, so that we can actually use our KCL and KVL and other, well, I don't know, node voltage analysis and other methods that we have learned in the electrical circuits analysis on those circuits, right? So basically the way it's done is that what we do is that we say that, well, if this is my transistor, I know that this is a voltage dependent current source. So I can say that if this is base, this is collector, and this is emitter, I can replace this. Let's say this transistor is connected to a bunch of resistors and capacitors and, well, other transistors as well, right? If I can redraw my circuit and replace this symbol that it's new to me, it's unfamiliar to me, and I'm not really comfortable writing current and voltage equations with it, I can actually replace it with this kind of a model. I can say that if I have a base here, I know that whatever voltage is between base and emitter, let's call that voltage VBE, right, is going to result in a current that is basically equal to IS exponential of VBE over VT, right? And then what is that current? Where is that current connected? Well, I know that this is a current that is flowing from collector to emitter because of the movement of electrons from emitter to collector. So this is collector, and I can call this terminal the emitter, right? Now, if I look at this model, first of all, there's something weird there that is like basically I have a gap here. There's no kind of an element connecting between these two. But then other than the weirdness of this, I can see that my currents don't add up because this model suggests that the current that I have in the collector, which is this one, is going to be equal to the current that is going to the emitter, right? I know that they're very similar to each other because, well, emitter's current is like basically the emitter current is really the addition of collector's current plus base current. And since base current is much smaller, let's say 1% of collector current, a lot of times you can actually approximate emitter current and collector current to be equal. But then this model is not about approximation. We want to be exact. And this is really trying to tell me that the base doesn't have any current, while I know that it does. But based on this model, the base current we cannot have a base current because, well, I have an open circuit here. And also it's telling me that collector and emitter have the same current. So I have to make some adjustment. The way I adjust this model to make it more accurate is that I say, well, I know that there's a diode between the PN junction, across the PN junction of base emitter. So I'm just going to put that diode here. And then I say that because I know the current of the base, so remember that collector current, IC, was IS exponential of VBE over VT. And I know that IB, the base current, is the collector current divided by beta, right? Divided by that large number. Always imagine 100 instead of beta unless another number is actually given specifically. So it's going to be IS divided by 100 or divided by beta exponential of VBE over VT. Great. So I'm talking about the current that is flowing from base emitter, and it is related. It is basically, it's the current expression turns out to be an exponential with the VBE here. So it is indeed a diode, right? Because I know that diode's current is ID is equal to some constant, this guy, times exponential of VD over VT. So having a diode is a great choice there. All I need to do is that I need to emphasize on the fact that this diode's reverse saturation current is actually IS divided by beta. If I write that down, then I know that, okay, if that's the reverse saturation current, then if you tell me that I only have this base current and the emitter current, the base terminal and emitter terminal, and there's a diode between them, and find the current of the diode, I can easily say that, well, current of a diode is IS exponential of VD over VT. So for this diode, the current is between base and emitter, so IBE is equal to the reverse saturation current here is actually IS divided by beta, exponential of VBE, which is the voltage across the diode, divided by VT. Okay, so that's how I get this. I'm going to just erase this because it's a side note. Okay, going back to what we were actually talking about. So I got my IC, I got my IB, and then I can see that if I add this guy and I add that guy, I'm going to get like the KCL at this node is going to give me IE, that is the correct expression. So IE is equal to IC plus IB, which is equal to IS times 1 plus 1 over beta times exponential of VBE over VT. Or I can call this beta plus 1 over beta times IS, and then the rest of the expression, which is what we had before. So this is basically what we call the large signal model of a transistor, meaning that as long as we are talking about DC voltages and currents, and as long as our signals are large enough, or like they're normal signals, like perhaps a better name for this is basically a normal signal model. The reason that we call it large signal model is in contrast with what we are going to talk about, which is called small signal model. So we are going to talk about how the transistor is operating, how the transistor operates when we have small perturbations in our voltages and currents, and we're going to call that model small signal model. Therefore, in contrast with that, we're going to call the normal kind of mode of operation of a transistor the large signal model, right? So it doesn't mean that like the signals have to be larger than a certain value for this to work. You can think of it as for normal voltages and currents, this is the model that you can always use. That there's a diode between base and emitter, and there's the transistor is really working like a voltage-dependent current source, with the dependence being exponential. Okay, so this is the way that your textbook is actually showing this model. So it's using a gray color to show the transistors to kind of like tell you that like how things are connected. So it doesn't mean that like you have all these connections at the same time. So the gray color is the transistor kind of shown in a shadow of it is shown, and then the black solid lines and components are showing the large signal model of the transistor, showing that basically this is the base current, this is the collector current, and the addition of the two is going to be the current through the emitter here. Okay, so let's solve an example which will give us a little bit of intuition about how things work in terms of current and voltage relationships in a transistor, and also what are our limitations in terms of increasing the size of a resistor or current of the collector or things like that, right? And it also makes us more familiar with all these equations and how to use them, right? Let's say that a circuit like this is given to us, right? So I have a transistor Q1. It is connected to the base of it is connected to a voltage source, and the voltage source has a value of 800 millivolts. The transistors IS and beta are also given to us. So IS of the transistor is 5 times 10 to the negative 17 amperes, which is not a surprise to be a very small number because we know that this is a reverse saturation current. And also beta is 100. Okay, also not a surprise. We have a resistor connected to the collector, RC. So it's between the collector terminal of the transistor, which is here, and some voltage source called VCC. And it's basically this voltage source has, or battery has, a 2 volts posted for it. And the emitter side of the transistor, or the emitter terminal, is connected to ground, right? So the first thing that the question is asking us is to check and verify if the device is indeed operating in the active mode. Okay, we said that to be in active mode, we need to have a VBE that is greater than 0, and we have to have a VBC that is smaller than 0, so that the base emitter junction is forward biased and base collector junction is reverse biased. So let's check that. So for VBE, it's actually quite simple because, well, we know that base is connected to 800 millivolts and emitter is connected to ground. So we know that VB is 0.8 volts, and VE is 0 volts. And based on these two, I can say that VBE is greater than 0. Great. How about VBC? Well, I know that what is the voltage of the base. How about the collector? So the voltage of the collector, meaning that the voltage at this node X, right? I'm interested in finding that. Another way to show that voltage is with the notation that we learned in electrical circuits is to actually say the voltage between this node and ground, right? So this is really V collector, or like Vx, right? So how can I find that? Well, I'm going to use KVL. So KVL tells me that plus 2 volts minus 500 current of the RC, which is the current that is flowing through the collector. So I'm just going to call that IC is, and then minus VC is going to be 0, right? Or in other words, VC is equal to 2 minus 500 IC. Great. Now all I need to know is what is IC, and here is where I actually use the voltage current relationship of my transistor that is operating in the active mode. I'm going to say that let's assume that, because I want to verify that this is in the active mode, so I'm going to assume that we are in the active mode, so I'm allowed to use this equation that IC is equal to IS exponential of VBE over VT. Okay, so assuming that I'm in, or well, not me, the transistor. So assuming that Q1 is in the active mode. Okay, so the nice thing about this is that all of these numbers or parameters values are given to us. So IS is 5 times 10 to the negative 17 exponential of VB is 0.8 and VT is 26 millivolts. So if I do the math for this, I'm going to get 1.153 milliamps. Okay, so this is all based on this equation. You can see that this value of IC is all I need to actually do the verification, but just for the fun of it, let's actually calculate IB and IC as well. So based on our equations, we know that IB is going to be IC divided by beta, so it's just going to be 1% of that, right? So it's going to be 11.53 microamp. And IE is going to be IC plus IB, so it's going to be the addition of the two, and slightly higher than IC. Remember that I said they're pretty much equal to each other within 1% or so. So IE turns out to be 1.165 milliamp. And you can see that 1.165 and 1.153 are pretty much similar to each other. The difference is just that 11 microamp. Now that I know these currents, let's go back and let's find out what is this VC. Calculating the VC, I'm going to find that VC is going to be 1.424 volts. Okay, based on this, so let's put an asterisk here, and knowing that VB is actually 0.8 volts, so VB being 0.8 volts and VC is equal to 1.424 volts, I can say with confidence that VBC is greater than smaller than 0. Therefore, so maybe I should have used this asterisk here. So based on let's say number 1 and number 2, I can say 1 and 2 tell me that I'm in the active mode. So Q1 is in active mode. Okay, so we just verified that. Now the second part of the question is telling me that determine the maximum value of RC. So meaning that if I could change this RC value, how much I could actually increase it until I actually get out of the active mode. So it is asking me to determine the maximum value of RC that permits operation in the active mode. Okay, so again, looking at the conditions of the active mode, which are these two here, I can see that, well, one of them is really independent of RC because VBE is not a function of change, like the value of that resistor. VB is constant, VE is constant, so I can be sure that my VBE is always going to be greater than 0. However, on the other side, for VBC, I can see that, well, again, VB is actually constant, but the collector's voltage is dependent on this equation, right? So I know that, so let's write it down. So part B, I know that VC is equal to 2 minus RC IC, right? The nice thing about this expression is that IC is also independent of the value of the resistor, right? Because this IC, I saw that it is actually dependent only on the VBE. That's the nice thing about the transistor. The current of the collector is independent of everything other than, it's only controlled by the base emitter voltage, let's say, right? So this tells me that this is equal to 2 minus RC times the IC that I found, which is 1.153 milliamps, right? Now, this way, I can actually I found the equation that relates my VC to RC. Now I know that if I increase my RC initially at this value, and if RC is 500, I figured out that my RC is going to be from the part A, I figured out my VC is going to be 1.4-ish volts, right? So I know that if I increase RC, I'm going to have, well, this term is going to increase. Therefore, the overall voltage at the collector is going to decrease. And it's going to decrease and decrease and decrease until the voltage of the collector is not greater than the voltage of the base. Therefore, I'm not in the active mode. So I need to find out how big RC should be so that 2 minus RC times this current is equal to the voltage that is at the base, which is 800 millivolts, right? So basically, I want to say that basically, I know that based on this, I can also write an expression that RC is really equal to VCC, the 2 volts, minus VC divided by IC, right? And since I want the VC, so I know that VCC is 2 volts, I want to find the RC that gives me a VC of 0.8 volts, and I know that the IC is actually 1.153 times 10 to the negative 3 because it's milliamp. If I calculate that, I'm going to get an RC of 1041 ohms. So I can increase the resistor from the 500 ohm value that it has right now up to all the way to 1041 ohms and still be in the active mode. If I go beyond this point, then what happens is that, so if RC becomes greater than 1041 ohms, therefore VC is no longer greater than VB. It becomes smaller than VB, therefore not in active mode. So this behavior is actually shown in this plot in the bottom left of the slide, right? So you can see that initially we were at this point where RC was 500 and the Vx or V collector was at 1.424 volts, right? If I decreased the resistor, or let's actually talk about what we did. If I increase the resistor, I can see that because the current is constant, the voltage drop across the resistor is going to be increased. Therefore, the voltage of the collector becomes smaller and smaller, and at some point it reaches the 800 millivolts or 0.8 volts. And that point is when RC is 1041. I cannot really continue that, because I cannot even say that after that we are going to have a smaller voltage here, because all of the stuff that I discussed above here was with the assumption that my transistor is in the active mode. The moment I go out of the active mode, then I cannot really model the behavior of my transistor the same way that I modeled here. So I don't know if it's going to go down, or if it's going to be constant, or if it's going to go up, right? So from this point forward, it's a big question mark for me, and we are going to discuss that. So we're going to talk about what happens to a transistor when it goes out of the active mode, right? But not just now. However, if I decided to actually decrease the RC and go the other way, you can imagine that the voltage across this resistor is going to be smaller and smaller and smaller until it becomes zero. When it becomes zero, it means that the two terminals across the resistor is going to have the same voltage. Since here I have 2 volts, therefore I have 2 volts here as well. When the current becomes zero, the resistor is kind of like a short circuit. That's why the voltage at the collector, or the Vx, becomes 2 volts when the RC becomes 0. Okay?